Hello, this is Mr. Steinerson, and I'm going to go through some basics with solving problems on ramps in this lesson. Please take out something to take notes on, whether it be digital notes or with paper. Follow along, write down one of the or two of the examples, and make sure you're following along with your notes today. Well, the first thing we want to review is this idea of net force and how it relates to our free body diagrams. So when we're taking a look at examples like this and you want to find the acceleration and there's multiple forces acting on an object, you want to make sure you combine the forces and therefore use that combined force as your net force. So hopefully you can see that there's 18 and 8 newtons here. The difference between those is 10, so we have a net force of 10 newtons in this direction. All right, so kind of in this diagonal direction. To find acceleration, we would go back to our F equals ma equation and solve for a. So acceleration is the net force divided by the mass. In this case, it's about 5 meters per second squared for a 2 kilogram block. All right, so a little bit of review there. We're going to use these ideas today a little bit more with ramps. All right, so some more review. Remember, acceleration is 0 when the net force is 0. So in that net force equation tells you if there's an acceleration or a change in velocity for your object. It wouldn't mean that their object is necessarily not moving, it just means it's not accelerating. So be careful with that distinction. And remember, if you have an acceleration, you can find the force that causes that by thinking about Newton's second law, F equals ma. A force of friction is related to the normal force by the coefficient of friction. And it's that number that tells you what type of surface is interacting with the other surface, and it depends on that type of surface. And the bigger your coefficient, the more friction happens between your two surfaces. We can use this equation, force of friction is equal to the coefficient, either static or kinetic, times our normal force. All right, a little bit more about some things that we've done to help us understand what's going on with these free body diagrams and friction. We are taking a look at objects sliding to a stop. If so, when we draw our free body diagram, we remember to include weight and normal force, but the only force that's causing it to stop is the force of friction. Therefore, the net force is equal to the force of friction. All right, so even if the object is continuing to move across the floor, if it's sliding to a stop, nothing else is causing it to, there's no other forces sideways acting on it, only friction, okay? The next case is our constant velocity, where maybe the frictional force and our applied force or our pulling force might be the same, might equal each other. And this would mean another net force is equal to 0, but the pull and the frictional force are identical. They're the same magnitude, okay, just opposite directions. All right. How does this relate to ramps? Well, when we take a close look at two cases where we could either have an object where it's stopped or moving at a constant velocity, so there's equilibrium of forces, or it might be accelerating down or up the ramp, okay? So if we look at that first case where it's stopped or in equilibrium, then we know that the frictional force and whatever force is causing it to pull down the ramp, so this parallel force that's along the ramp surface must be equal. So in this case, the force of friction equals the force parallel, kind of coming back to that thing we just saw about moving at a constant velocity or at rest, equilibrium. Okay. The other thing to take a look at is what would happen if we are accelerating downwards. All right, so I'm going to get rid of this arrow and I'm going to include one for accelerating down. Well, if it's accelerating in the downward direction, then that parallel force has to be larger. So in this case, the net force would exist, where we have the sum of our parallel force and the frictional force, okay? That difference, because they're pointing in opposite directions, would equal my net force, okay? Well, if we have two strings or two objects pulling on that thing to accelerate it downwards, we might have another force acting on it as well. So I might even draw in another parallel force here, another applied force. Then if we're solving our net force equation, we can add in those additional forces. So we might have the force in blue, we might have the green force, and then we might have the frictional force that's subtracted from both of those. Okay, so building that net force equation, we look at our free body diagrams to figure out what forces are acting on the objects. All right, how does this relate to ramps? Well, when we're looking at our ramp, we have to be kind of mindful of the axis that we're using, because we're going to talk about a force that's parallel and perpendicular to the motion. So we're going to break our weight force down into its components. Weight is always directed straight downwards. We can take a parallel component of that or a vertical component of that, perpendicular component of that, by using our sines and cosines. The angle of the ramp is equal to this inside angle right here and right here. Okay, so those angles are the same. Then we can use our sines and cosines to figure out what magnitude the perpendicular has, the force weight times the cosine of the angle, or the parallel force weight times the sine of the angle. So just a little bit of review, sines and cosines will come into play to help us break down the force weight vectors. And now normal force and friction forces are going to be present on ramps as well. And remember, the normal force is the force that's perpendicular to the surface. When we have an angled or an inclined surface, that perpendicular is no longer the weight because it's not perpendicular to that straight down weight force. We have to use the component that we just talked about, the perpendicular component here. Then that would equal the normal force. The frictional force can be solved by taking the coefficient times the normal force. So once we find out what that perpendicular component is, we can help us then use that to find our frictional force. Okay, so let's do one example together here. We have some ramps in equilibrium. We need to come up with our net force equation. Okay, when it's in equilibrium, remember the net force is equal to 0. So our whole net force equation will equal 0 in this case. So if we take a look at the force is moving along the ramp, so we have a parallel force and we have a frictional force. That minus the frictional force, whatever it is, has to equal 0. So if I rearrange this slightly, I know then that my force parallel down the ramp is exactly equal to my force of friction along the ramp. Okay, so when we're solving, we're trying to figure out what this is. Remember, in equilibrium, the net forces are 0. Our acceleration is also 0. The normal force is equal to our perpendicular force, like we've talked about, and the force of friction is equal to the parallel force. Once again, we can solve that using our sines and cosines based off of what we know from the weight force. So these become kind of like a bit of a puzzle, knowing which piece matches which part of the equations. All right. Now, if we have something that is accelerating, once again, we'll come back to this net force idea, right? Force net is the force of friction, okay, and the force parallel combining together, all right? So if I look at my parallel force, force parallel minus force friction is going to equal the mass times the acceleration of the block, okay? So I need to be able to identify what those are and then work backwards to figure out my acceleration. Okay, so the force net is going to be my parallel force minus my frictional force. The parallel force is larger, so it should accelerate down the ramp. Acceleration then is going to be whatever that net force is divided by mass. And my normal force is equal to my perpendicular, and my force of friction is the coefficient times normal force. Okay, so we're going to put these practices to action here, and I have a ramp that is at 40 degrees, and so you can see the angle here. That means this interior angle is also 40 degrees. The coefficient on the ramp is 0.15, okay? And we're going to figure out what the acceleration down the ramp is, okay? So the weight in this case, all right, so we have a mass, we have a 10 kilogram mass, so the weight is 9.8 or 98 newtons, sorry. So when we take a look at the mass, we're able to figure that out. We know it's 10 kilograms. That's just given in the problem often. The weight is 98 newtons, 10 times 9.8. The force perpendicular is 75. Now I got that by taking my weight force, my 98, times the cosine of the angle, okay? My perpendicular, I'm going to do something very similar, but I'm just going to do it with sine. My normal force is going to be related to one of the forces I have on here already. All right, think back. The normal force is always perpendicular to the surface. So I've already figured out a perpendicular component, that's this one right here, so that should equal my normal force. And it sure does, 75 newtons and 75 newtons. My force of friction is going to be equal to the coefficient, which we know here is 0.15, times that normal force, times 75. So my force of friction becomes about, let's see right here, 11.25, sorry about that. Now my net force, if I put in my force of friction and the component of 63 newtons, that's my parallel component, I'm just going to draw that in right here. So this is 63 newtons. My force of friction, which we just solved, is coming back this way. I'm going to add that arrow on here so we can kind of see that. This one is smaller, it's 11.25 newtons, and it's in the opposite direction. So to find my net force, I'm going to subtract those two, 63 minus 11.25, then that becomes my the answer that I divide by the mass to figure out what my acceleration is. Okay, remember the mass was 10 kilograms, so I'm just dividing that net force by 10 to get 5.175. All right, great. Let me know as you're practicing these problems, going through the examples on Quest and your homework, if you come across any questions, but make sure you identify the different forces based on the free body diagrams and using what you know between the relationship between the normal force, the perpendicular force, and the parallel force and any maybe forces that are acting along the motion like friction. Thanks and have a great day.